So this morning when we were proving the 3' theorem of Vinogradov, we said we were breaking this up into two parts, the major arcs and the minor arcs, and we are still estimating the major arcs. So this part we have finished. We have reached this formula, and then this part here in Q5 5Q cubed, and this one the Ramanujan sum. This whole thing we have seen that this can be estimated by big O of this part. This can be estimated as big O of log minus b plus 1 of n. And now, therefore, it remains to see how we are going to, what we are going to do with the second part, the integral that is over there. So let's do this part. Let's do the second part. This part is 1 by, so we have now t beta, you remember this t beta that came up, t beta in a cube, and then we have exponential. So now we are going to do this one here. This one. Exponential minus n beta d beta, and the integral is between minus 1 by q and plus 1 by q. Okay. So this is the, so this can be written as, we can change the minus 1 by q to plus 1 by q, and this is 0 to 1, t beta cube exponential minus n beta d beta plus, I take an error term, big O of 1 by q, the same integral, but now I'm going from 1 by q to 1 minus 1 by q, and d beta cube d beta. So the question will be how to take care of this t beta. Now, t beta is the sum of a geometric series by its definition. This was in the beginning of today's, this morning, we talked about it. So, t beta is the sum of a geometric series, and therefore we know how to sum geometric series, and therefore we can say something more about it. So, t beta, this is equal to exponential n plus 1 beta minus exponential beta with beta minus 1. Okay. And what is this equal to? I mean, I want to write some bound for it. So this is big O of minimum of n and 1 by the distance beta on r z. So what is this? This symbol here, this means that this is the distance of whatever is in here of this to the nearest integer. You must have seen such things in the Diophantine approximations. Okay. So now let's write this again. This minus 1 by q, this one here. Minus 1 by q plus 1 by q. T beta cubed, what you see over there. T beta cubed, exponential minus n beta, T beta, what is in orange here. So, so this is equal to, write it again. So T beta has found some meaning. So now this one, so I want to estimate this one. Okay. So, let me write it again. Here. So T beta, I have T beta as a cube. Then I have this exponential. That's an integral between minus 1 by q and plus 1 by q. That's this one. Yeah. And this one is equal to, therefore, write the first term. So this is equal to 0 to 1. T beta cubed, exponential n beta, stays the same, plus we saw how the T beta behaves. So this is equal to big O of q square, which I can also write as big O of n square log 4 b n. Okay. So I want to still continue to work on this. Now forget the error part and come only to this one. Term by term I pull out and try to see how good it can become, how precise it can become. So here we are. Okay. All this has been taken into account. We are still looking at the T beta cubed. The first term over there, T beta cubed, exponential minus n beta, d beta. So this is half n square plus big O of n square by the error that I found there, log 4b, log b minus 1. Alright. So now, b minus 1, no, 4b. Okay. So now, let's go back, put this back into the, finally, I put all this back into the fixed formula, okay, then S alpha cube, we'll write it again in pink. So S alpha cube exponential minus n alpha. You remember that we have pulled out one part, pulled out the other part, and done some nice things to them. So the first part we saw, we got our singular series from them. The singular series was what we were looking for. Yeah. So this is equal to, so this one, yeah. This is also over. Yeah. So this one, d alpha. So remember that this part we got the singular series from here. So we write it. So this will equal to half S n n square. And then what remains is you have a 4b here and you have a b minus 1 there. So that's the denominant one. So we go n square log b minus 1 n. Yeah, this is 4b and this is b minus 1. So that's the best we can do with the major arcs. So now that's small, okay? This is small. You have, we saw this right in the beginning, the singular series, and this is not big, but this is major arcs. So what remains to be done is, now we look for the minor arcs, okay? So Vinogradov's theorem would follow if the minor, I haven't finished with the little m. So now notice, so that's the end of major arcs, okay? Now, and so you have realized that we use only the things that we knew till now. I mean, we knew, maybe that's saying a lot, but we have seen. It's not, we didn't bring in anything, any foreign element into the story. They have been developed. All the tools that have been used have been already developed. So that these are the prime number theorem for arithmetic progression, the zero-free region, and the explicit form. Okay. And now I want to talk about minor arcs. I have told you that here we are going to do some hand waving, a bit of hand waving. So that's because the exponential sums over primes that Vinogradov studied, that we didn't study. I mean, we didn't make a serious, we didn't have a serious look at it. So that's a question of choice, but we could not do it. But we can still have an idea of how it works with the minor arcs. Okay. So we will use Vaughan's identity here. I think Vaughan simplified Vinogradov's proof. So with minor arc, so we use Vaughan's identity. Same Vaughan who wrote Montgomery and Vaughan. Okay. I suppose he's still alive. Yes. Then he is. So this will be in the context of exponential sums over primes And here for this, and I will give you a reference. You can revalidate it for multiplicative number theory. I think chapter 24 and 25. I think anyway the chapters are very, very short. So multiplicative number theory. Or Ivanich-Kowalski. What is the name of the book? Maybe it's called Introduction to Analytic Number Theory. All these books have the same name. They're called Introduction to Analytic Number Theory. I don't remember exactly the name of this book. I think so. It's not an introduction. So these are the references that I know. You have studied this from Nathanson's book. Which one? Additive basis? Okay. I don't remember having studied it from there. But I don't know if you like it, you can do it. But I mean, their report is certainly older. So you can find Davenport has 2 chapters on exponential sums of times, but the chapters are very short, maybe 4 pages. So not so many details. And so this part I will. So as I said, I will not have the time to do this seriously. So the exponential sums come from there, and so I would suggest that you do study exponential sums at some point or the other, because you will need exponential sums over time. You need them if you want to continue to work on these kind of areas. And then you will find that there are different types of sums, type 1, type 2, type 3, type 4, and which of them contributes more, which of them contributes less, etc. It's all a bit scary. So that's what we have here for the major. Let's assume that we have understood something about the major. Now the minor arcs. Okay. So minor arcs, what do we notice? We have already seen that there exist minor arcs. It's not as if everything is taken out by the major arc. So remember again that the last formula that we had, the left-hand side of that, what was it doing? It had S alpha cubed exponential minus n alpha d alpha. Yeah, this was the one. But this time we want to see this over the minors. Okay? So these are the minors. Okay? This is small n. It's quite difficult to distinguish this on the board between what's a big Gothic m and what is a small Gothic m. It's a bit difficult. But we are talking about minor arcs. So this is small, okay? Small. So this one, if we want to count this, then this is going to be less than or equal to the maximum of S alpha, okay, over this little n, Okay. And then one of them have come here, and then there's a second one. So this is S alpha square D alpha over the same. Okay. So if this is over little f, then I can as well do this over 0 to 1 and take the S alpha square D alpha and keep this as this. So my aim is to get a bound. Yeah? Now we are going to look at the square. What about the square? This one. How do you define this? This one, how do you define it? So S of alpha square, that's this one, between 0 and 1, D alpha. So there's a square. Now we are going to have two. We are going to have two conjugates, right? So lambda k1 and lambda k2. So we write this as lambda k1 and lambda k2. All right, k1 and k2 will both be bounded by my little f. Okay. The capital, this one. Yeah. K1 is less than capital N and K2 is less than capital N. Okay. And then if I take if I take the lambda K1, lambda K2, so what I will get is order of big O of no, from getting a big O, I will get exponential. So exponential K1 minus K2 alpha 0 to 1 d alpha. This is equal to, so lambda k, now instead of this I can take lambda k itself, but square, instead of having two variables, I can write this as one single variable, and this is equal to big O of n log n. So we need a bound now for f of alpha. Okay. So here is the part that we are going to do some hand waving. Okay. We are going to do some hand waving here, but you can still get an idea of what we're talking about. To bound S of alpha. Till now, we haven't done anything complicated. I mean, we haven't done anything that is unknown. So now, where is alpha? Where is our alpha? This alpha, you remember? Where is this alpha? Here. So yeah, so it is in the minor arc. Yeah, it is in the minor arc. Therefore, it is we can take its distance from rational number. And you know that I hope we know that the distance between alpha and the rational number a by q, a and q are given to us. Okay? So this one, alpha is the real, and the distance between alpha and a by q, okay, what is it? what is its relation? It should be, so it's greater than 1 by q. Okay. It's greater than 1 by q. And that's log 2 beta n by capital N for all q, which is for all little q, which is less than equal to p by my definition. Why? Which definition? Which definition? Definition of what? Alpha. Where is alpha? Alpha is here. Alpha is not in the major arc. Alpha is in the minor. Okay. Therefore, q is less than equal to p if alpha belongs to n. Okay. And here is the part which comes apart now, which I will not do in detail. I want I have S of alpha. I want to find a bound for it, and therefore, if I take the bound means I take this alpha minus a by q, okay, and I take the infimum of q between 1 and p, because q is between 1 and p, then this is greater than log, so I would write it here, that would follow from log 2b by n. That's the part that I'm cheating, okay? So, I'm not cheating because it's false, it's true. I'm cheating because I'm not giving it, okay? So, I'm not giving you the proof. So now, I have a lambda n. So, lambda n is, you remember, it's the von Mongol. Therefore, lambda n is log d mu n by d, yeah, log d, because the convolution, and mu. So mu, the Mobius function mu, this is defined on integers, but I will have to work now on x. So I'll say that if x is a non-integer, then mu of x is 0. So mu of x, I say that mu of x is 0 if x is outside Z. Okay. In that case, lambda n can be written as this lambda n. It can be written as log d mu n by d. But now I don't say that d divides n. I say for all d up to n. Alright. Unless I said that mu of x has a meaning outside the integers, I would not be able to say this. Let's go back to our S of alpha, our S of alpha, which we were trying to understand right from the beginning. So S of alpha, this is equal to n less than equal to n lambda n exponential n alpha. Okay, which is, I will write this one back now. So easy here to do that. So this becomes, the first sum remains S of alpha. You have a first sum cumulative length, and then for lambda n, we take a second sum. Okay, so delta less than equal to n log delta mu n by delta exponential n. Okay, so separate this out. Log delta can go out, and log delta less than equal to n, then something else, sum n less than equal to n by delta, and mu of n, this mu of n, exponential n delta I. Okay. Now comes this somehow mysterious stuff. Okay, which we bring in here. So if the infimum of q between 1 and p, alpha minus a by q, if this is greater than log 2b n bar, okay, then I can substitute this. Then I can substitute this back into my s, and therefore I can write infimum of q alpha, now this q between 1, and this time it's not between p, but I'm writing it as log delta n. This will be greater than log 4b n by n. So then we have done everything, and all that, so you choose your b as promised, and choose b to be. We said we were going to choose b as a function of the bit a, which was there right at the beginning, and here we can take it to be, for example, 9 times 8 plus 6. Another one we have done, but the point is that you can find it. This b therefore exists, therefore we have estimated the minor arc. So we estimated the major arc, we estimated the minor arc. You have a question?
Yeah, you have to treat the lemma, right? I mean, if they are definitely inequality satisfied, that means the infimum function is bounded by this, bounded below by this, right?
Yeah.
Then if this condition is satisfied, then we need to write the exponential.
Exactly. But I was not going to prove that lemma.
So maybe you have also stated that lemma.
Yeah, I could have stated that lemma, but I didn't state it. So it's there. It's there. So somehow it's a little bit. The part that's a little bit mysterious is this one. Yeah. So it was a little. It's not that. It's not as clear as everything else. Yeah. And therefore we have finished the piece of I'm a bit unclear about chain. What did chain do?
That was for sufficiently large decade number.
Yeah.
Not when he proved that sufficiently large decade number can be written as sum of a prime and a number which has at most two prime factors.
At most two prime factors. Yeah. So Winograd of chain, they had already did the part of the work, most important part of the work was this, to have done this. Closing up again, I'm not saying it's not, it's trivial affair, but this is the fundamental work. Now in biological graph, we don't have, where is the problem? I mean, of course, people can ask, if you can do this for 3 primes, why can't we do it for 2 primes? Yeah, so where do you think the problem is for the, I mean, at least it will not be done by this method, that's clear. And but that's maybe not so clear to people, right? That it cannot be done by.
I can see the minor calculation here only, but
yeah, it's
that was Q.
Yeah.
And one part is taken out.
The fact that there was a cube, this helped us bring out 1 and 2. And when you do square, you can't do that anymore.
I mean, the square part is like trivial.
Yeah.
Using the prime number theorem.
Exactly.
And the non-trivial cancellation comes from the exponential law. Like
exactly. That is not there for the binary. So it is clear that the binary Goldbach will not be proved like this. Okay, not by this. If binary Goldbach is perhaps going to be proved someday, but disproved. But not like this. This method will not can go for to this case. It's not. So yeah, maybe you should do also an exercise, shouldn't you? I think you should do an exercise. Simple exercise. You prove the Vaughan's identity. Prove the Vaughan's identity. That's not a difficult thing. Okay, it's not difficult at all. So if you came for this, since you came for this course and you learned 3 important theorems, I think you learned 3 important theorems. I think it's worth coming for the course. Yeah. I mean, 3 theorems of this status. Yeah. Prime number theorem for arithmetic. Prime number theorem you would have learned anyway. That's not. But for arithmetic progression, it's probably not done all the time. And yeah, that makes it only 2 zeros. No, 0 free regions. 0 free regions. Okay, so prove Vaughan's identity, which says that Vaughan's identity, which says that if u, v, and n be positive integers, let the product of u and v be less than equal to n. Then, for all n, little n, less than equal to big N, mu of n can be written as, this mu is Mobius mu, mu b, mu c, bc divides n, b less than equal to u, c less than equal to b, plus mu b, mu c, bc divides n. So the complement of this, b greater than u and c greater than. If you prove this, you get your dinner. Do they get dinner if they can't prove it? But anyway, it's not possible to not prove this is true. Yeah? V, C is greater than V. So the combination of B and C with these four criteria will give you four criteria, four possibilities. Maybe you can write it as these four possibilities. So if you, for example, have something like this, so mu of n, okay. Now mu of n is equal to, mu of n can be written as mu of B times mu of C. Yeah, for all BC, which is equal to n, or which divides n. BC that divides n, okay. So here, B is less than equal to U. Okay, BC that divides n, and this is correct, okay. Every time you take a product, BC divides n, you can write it as mu B, mu C, okay, and take the sum over the whole thing. Now, suppose I write this as with the criteria that are being asked for. BC divides n, B less than U, C less than V, B greater than U, C greater than V. So suppose I take B less than equal to U, B less than equal to U, and C less than equal to V, okay? Then I change one of them, leave the other one. What should I get now? BC divides n, B less than equal to U, its complement will be B greater than U, yeah? And this one you can keep as it is. Then here, BC divides n, B greater than, keep the B same and change the V, C, and finally change both. BC divides n, B greater than U, and C greater than V. Is that okay? This possibility exists. And always this is for mu B, mu C. Mu B, mu C, mu B, mu C, mu B, mu C. Okay. You can call them as different sums. You can call them as 1, plus S2 plus S3 plus S4. Okay. And what do you see? Which ones appear over there? Mu of n, you have the first one and you have the fourth one. So you don't have the second and the third one. Where have they gone? What about what about the second and the third one? What are they? Why did they disappear? What do I notice? Do you see any relation between the second and the third one? S2 and S3? Yeah? Are they, is there some relation clear between the two of them? Huh? What about? What did you see? They are the same because B and C are symmetric. Okay, there's nothing special about B or C. They are interchangeable. So in one case, B is less than U, C is less than V, and the case is B is less than equal to U, C greater than equal to V. Therefore, T2 and S2 and S3 are the same. Yeah? S2 is equal to S3 because because B and C are symmetric. They are symmetric in B and C. Do you agree? B and C. Yeah? No difficulty in it. What is the relation between S1 and S2, for example? S1 and so S2 and S3 are the same. Yeah. And this is the negative of the first one. Yeah. So S1 is equal to minus S2. So these two go away because you see why S1 is equal to minus S2? Because I can write this as mu of n is mu b mu c, bc divides n, etc. All those things I can write. Mu of n is mu b mu c. Okay. Bc divides n and c is less than or equal to v. Yeah. So, and this is equal to mu of c is a delta Cn, which means either 1 or 0. C divides n. C is less than or equal to V. And that's equal to 0 if uh, if V is less than equal to N. Okay? And therefore, these two disappear. What is left is T1 plus T4. Okay? 2 and 3 disappear. And mu of n is T1
plus T4. No, S1. You said something? Here, since S2 and S3 are equal, yeah, I'm trying to see what is the difference between S1 and S2. What did you say?
How do you interchange
Interchange what?
B and C?
Well, that's what I do there. Instead of taking mu B, I take, so I forget one of them. I forget one of the conditions, yeah, and keep only the V as the only condition. If V is the only condition, then everything can be expressed in terms of C and N.
No, because the identity was mu of n is x1 plus s4.
Yeah.
So basically, the middle two terms should be 0. I mean,
S2 and S3 are not, S2 and S3 are not, S2 plus S3 is 0, yeah? No, S2 plus, wait, no, S2 and S3 should not be 0. Why should they be 0? S2 is equal to S3. But that doesn't mean they are 0. Yes. So I don't need S1 is equal to minus S2. Because that I get over there.
and we can prove that s2 equal to 0.
Yeah.
Suppose that we want to pick B outside the summation.
Yeah.
Take S2 sum over B, and inside the summation there is C. So that means C runs over, C divides n by B.
C divides n by B.
And C is less than B. And n by B is actually less than B.
Yeah.
So basically that sums over all the divisors. So the inner sum
Then
of C divides n mu of C times.
Then you have the mu of B.
If n is greater than or.
Yeah. So I don't need S1 is equal to minus S2. Yeah.
So n by B is actually greater than or, so that summation of
Right.
is 0.
This is not required. This is not required. But S2 and S3 being equal means it's enough to show it for one of them. Yeah. S2 and S3 are equal and they're 0. So after that, S1 plus S4 is the only one which are left. Yeah. Those two are equal to 0.
Yeah. I think that calculation is correct. S2 equal to S3 should be 0.
I somehow thought S1 had to be used. So if S1 is minus S2, then S1 plus S2 will be 0. Or S1 plus S3 will be 0. Which will be equal to S2 plus S4. Yeah, I think that's superfluous. I don't need S1 to be equal to minus S3.
And is it correct that S2 should be 0?
Looks like. But I thought I didn't need it. S2 should be 0 because here, but maybe you can do it both ways. Perhaps both are correct. S1, huh?
How do you need to say the sum and between two sums should be 0? Like either S1, S2 plus S3 equal to 0.
Yeah.
Maybe both of them should be 0. Because we need S1 plus S4.
Now it is true that S2 is S3. Yeah. So if one of them is 0, the other one has to be 0.
I did a calculation like that S2 equal to 0. I don't think it's correct.
Yeah, let's think about it for a minute. Hmm?
Equal to
There is just one choice. 3 and 2.
so okay, you are taking n to be 6. U2
Minus
S3.
S4.
Fine.
So this S3 minus S4.
Just one choice. You must be 3.
Okay, B is greater than, so B is 3. Okay, and B could be
C is less than B.
B could be 6. But maybe, but the sum should be 0 somehow.
C, it doesn't matter. It's one of the divisors. One of the divisors. So you don't need to have the range to be the same. You don't have to need to have the range to be the same. What you are saying is one is greater than the given something and the other one is small.
So one divisor is greater than B.
Yes.
Another is less than U.
Yes.
That should be in both the sum, right? So in one sum, one divisor is greater than B, other is less than U. But in the other sum, one divisor is greater than U instead of B.
Think about it. You take T and think about it. I think there's something very simple in the story which